In the previous lecture, we saw the phasor diagram for a practical transformer when there is no load connected at the output. In this lecture, we will analyze and develop the phasor diagram for a transformer under the loaded condition. To understand this, we will consider three cases: transformer with no winding resistance and no leakage flux, transformer with winding resistance but no leakage flux, transformer with both winding resistance and leakage flux. Each case will be analyzed for three different types of load: resistive, inductive and capacitive. At first, we will discuss the transformer with no winding resistance and leakage flux. In this case, the transformer somewhat behaves like ideal, meaning it has no winding resistance and no leakage flux. This implies that there are no copper losses in the windings and all the flux generated by the primary winding links perfectly with the secondary winding or no leakage flux, and the transformer is lossless and the core is infinitely permeable with no core losses. So here the supply voltage in the primary winding is V1 and the induced voltage in the primary winding is E1 and the induced voltage in the secondary winding is E2, and the voltage across the load connected to the secondary winding is V2. I1 is the total current in the primary winding, I2 is the total current in the secondary winding, I0 is the no load current in the primary winding, which consists of two components, IC and IM. Phi 2, the phase angle between the secondary current and the secondary induced voltage E2, and phi 1 is the phase angle between the primary current and primary induced voltage E1. In this scenario, there is no winding resistance, that means R1 equal to R2 equal to 0. There is no voltage drop due to resistance in primary or secondary windings. There is no leakage flux, meaning that X1 is equal to X2 equal to 0, or all the flux links both windings perfectly, so there is no leakage reactance. The transformer has iron losses, hysteresis and eddy current losses, which are accounted by the no load current I0. Now the transformer with no winding resistance and no leakage flux, if we close the switch, a current will flow through the load, and this current is generated due to the induced voltage in the secondary winding. Now let us understand the voltage relationship for this loaded condition. Since there is no winding resistance or leakage reactance, thus the primary supply voltage V1 is equal to induced voltage E1 or V1 equal to E1, and similarly the secondary induced voltage E2 is equal to the load voltage V2 or E2 equal to V2, and the turns ratio K relates the primary and secondary voltages, or E1 by E2 is equal to N1 by N2 is equal to K. If we close the switch, there will be a current through the load, and this current I2 will be generated due to the induced voltage in the secondary winding. This current in the secondary flows through the load as the transformer is loaded. The angle between the secondary current I2 and the voltage across the load V2 is phi 2. So the secondary power factor is cos phi 2, and this angle phi 2 depends on the type of the load. If the load is purely resistive, then the angle phi 2 is equal to 0. If the load is purely capacitive, then the secondary current I2 leads the load voltage V2 by an angle of 90 degree, and if the load is inductive, then the secondary current I2 lags the load voltage V2 by an angle of 90 degree, and if the load is not purely resistive or purely capacitive, then leading and lagging will be of an angle of phi 2. Voltage across the load in the secondary winding V2. Since the winding resistance R2 is equal to 0 and the leakage reactance X2 is equal to 0, there is the voltage drop across the resistance R2 or the leakage reactance X2. The voltage drop across resistance R2 is given by I2 into R2, which is equal to 0, and the voltage drop across the leakage resistance X2 is given by J I2 into X2, which is also equal to 0. The voltage across the load is V2 will be equal to the induced voltage in the secondary winding, or E2, so we can say that V2 is equal to E2. The total current in the primary winding is equal to I1. It supplies the no load current, which is a small current I0 that transformer draws from the supply under no load condition, and it is denoted by I0. This current has two components. First component or in phase component is in phase with the alternating supply voltage V1, and this component is denoted by IC, which accounts for core losses and eddy current losses. The second component or magnetizing component lags behind the alternating supply voltage V1, and it is denoted by IM. This current is responsible for mutual flux in the core. The primary current I1 also supplies an additional current I2 prime. When the transformer is loaded, the secondary current I2 flows through the load. This current creates a demagnetizing effect that opposes the main flux phi m. To counteract this demagnetizing effect, primary winding draws an additional current I2 prime. The value of this current is such that N1 I2 prime is equal to N2 I2, where N1 and N2 are the number of turns in primary and secondary winding respectively, and I2 prime is the load component of the primary current given by I2 prime is equal to N2 by N1 into I2, or I2 by K. The angle between the supply voltage V1 and the total primary current I1 is equal to phi 1. So the primary power factor is cos phi 1. maintaining constant flux phi m in the main core. The current denoted by I2 flows in the secondary winding. It is generated due to the induced voltage in the secondary winding, or E2. The induced voltage E2 is produced by the flux generated in the main core of the transformer. Now, according to the Lenz's law, the current flowing in the secondary winding I2 will oppose its cause. The cause of the current in the secondary winding is the main flux phi m circulating throughout the core. This current in the secondary winding I2 generates a flux that opposes the main flux phi m. Let's denote the flux generated in the secondary winding due to the current I2 as phi 2. This flux phi 2 will try to oppose the main flux phi m by attempting to decrease it. However, we know a transformer is a constant flux device. That means the flux in the main core phi m must remain constant in the ideal case or nearly constant in the practical cases. To keep the flux in the main core, which is phi m, constant, we need to increase the magnetomotive force supplied to the core from the primary winding. This requires an additional current to flow in the primary winding, which is added to the existing current I0. This extra current generates additional MMF in the primary winding. This additional MMF produces an extra flux that counteracts the flux generated in the secondary winding due to the secondary current I2, and the flux generated is phi 2. Let's denote this extra current in the primary winding as I2 prime. The magnitude of this I2 prime is such that MMF in the primary winding due to I2 prime is equal to MMF in the secondary winding due to I2. Or mathematically, this can be expressed as N1 into I2 prime is equal to N2 into I2. Solving for I2 prime will give us I2 prime is equal to N2 by N1 into I2, or in terms of turns ratio, I2 prime is equal to I2 by K. Extra flux and balance of MMF equation. The additional current I2 prime in the primary winding generates an additional flux denoted by phi 2 prime. This additional flux of phi 2 prime is equal in magnitude to the flux generated by the secondary winding current I2, or which is phi 2, but this flux acts in the opposite direction of phi 2. So the direction of phi 2 prime exactly opposite to the direction of phi 2. Thus the extra flux phi 2 prime compensates for the flux phi 2 generated in the secondary winding due to the load current I2. This ensures that the flux generated in the primary core phi m remains constant. So the total magnetomotive force developed in the primary winding is the sum of magnetomotive force under the no load condition, which is N1 into I0, and the extra magnetomotive force required to counteract the secondary winding current, which is N2 into I2. So mathematically, this can be expressed as N1 I1 is equal to N1 I0 plus N2 I2. We solving for the I1, we will get I0 plus N2 by I1 into I2. In terms of additional current I2 prime, we can write I1 is equal to I0 plus I2 prime, where I2 prime is equal to N1 by N2 into I2, and I2 prime is the load component of the primary current. Let's draw the phasor diagram. We will take the main flux phi mt as reference phasor. The induced voltages E1 in the primary winding and the E2 in the secondary winding lag behind the main flux phi mt by an angle of 90 degree. We can draw this induced voltage E1 in the primary winding as minus E1 by shifting this E1 phasor by an angle of 180 degrees. Since the resistance and the leakage reactance of the secondary winding are negligible, we can write induced voltage E2 in the secondary winding is equal to voltage across the load V2. This means that induced voltage E2 in the secondary winding is equal to the voltage across the load V2. Similarly, on the primary side, the resistance and leakage reactance are also negligible. Therefore, we can write V1 equal to minus E1. This minus sign indicates that the outlet voltage V1 is equal in magnitude but opposite in phase to the induced voltage E1 due to the Lenz's law. Since a load is connected to the secondary winding, a current I2 flows through it. The phase relationship between the current I2 and the secondary voltage E2 depends on the type of load. For purely resistive load, the secondary current I2 is in phase with the E2, or phase angle phi 2 is equal to 0 degree. For purely capacitive load, the secondary current I2 leads the induced voltage E2 by an angle of 90 degree. For purely inductive load, the secondary current I2 lags behind the induced voltage E2 by an angle of 90 degree. For resistive inductive or RL load, the secondary current I2 lags behind the induced voltage E2 by an angle of phi 2, where phi 2 lies between 0 and 90 degree. For capacitive, resistive or RC load, the secondary current I2 leads the induced voltage E2 by an angle of phi 2, where phi 2 lies between 0 and 90 degree. In an inductive, capacitive or LC load, if the inductive reactance dominates, then secondary current I2 lags the induced voltage E2 by an angle of phi 2. This is similar to the RL load case. If the capacitive reactance dominates, then the secondary current I2 leads the induced voltage E2 by an angle of phi 2. This is similar to the RC load case. For a resonant load or RLC load at resonance, the inductive and the capacitive reactance cancels each other out and the load behaves as purely resistive. In this case, the secondary current I2 is in phase with the induced voltage E2. This is similar to the purely resistive load case. If the load is nonlinear in nature, electronic devices like rectifiers or inverters, the current waveform may be distorted and the secondary current I2 will have harmonics. The phase relationship between the secondary current I2 and induced voltage E2 depend on the specific characteristics of the nonlinear load. Now, in the primary winding, the current flowing through the primary coil is I1. It is consists of two components, the no-load current I0, additional current due to the secondary current I2. The no-load current I0 flows through the shunt branch and it has two components, IC and IM. The voltage across the shunt branch is equal to V1 or E1. The shunt branches consist of resistance and inductance forming an RL circuit. An RL circuit is inherently lagging in nature. Therefore, the current I0 will lag the alternating supply voltage V1 by an angle of phi 0. The no-load current I0 has two components. This IC is called the in-phase current. It is also known as loss component current or IW. This IW or IC is purely resistive. It is in phase with the alternating supply voltage V1 and it has an angle of 0 degree. It is also very small in magnitude and it is given as IC is equal to I0 cos phi 0. The magnetizing current Im is purely inductive. It lags behind the alternating supply voltage V1 by an angle of 90 degree. It is very small in magnitude and it is given by Im is equal to I0 sin phi 0. Additionally, there is a current I2 prime that counteract the demagnetizing effect of the secondary current I2. This current is equal in magnitude and opposite in direction to the current in the secondary winding or I2. Therefore, the primary current I1 is a sum of I0 and I2 prime, or I1 is equal to I0 plus I2 prime. Let's see the phasor diagram for the three load cases: purely resistive, inductive or RL circuit, capacitive or RC loads. For purely resistive load, the secondary current I2 is in phase with the induced voltage E2 or the load voltage V2, and the corresponding reflected primary current I2 prime will be in phase with the primary voltage V1. Total primary current I1 is the vector sum of the no-load current I0 and the reflected primary current I2 prime, resulting in a phase angle of phi 1 with respect to the supply voltage V1. For inductive load or RL load, the secondary current I2 lags the induced voltage E2 or load voltage V2 by an angle of phi 2, and the corresponding reflected primary current I2 prime will lead primary voltage V1 by the same angle phi 2. The total primary current I1 is the vector sum of the no-load current I0 and the reflected current I2 prime, leading to a phase angle of phi 1 with respect to the voltage V1. For the capacitive load or RC load, the secondary current I2 leads the induced voltage E2 or V2 by an angle of phi 2. The corresponding reflected primary current I2 prime will lag the primary voltage V1 by the same angle phi 2. The total primary current I1 is the vector sum of the no-load current I0 and the reflected current I2 prime, resulting in a phase angle of phi 1. From here, we can determine the primary power factor cos phi 1. It is determined by cos phi 1 is equal to I0 cos phi 0 plus I1 I2 prime cos phi 1 divided by I1. If IV and IH represent the vertical and horizontal components of primary current I1 respectively, these components are obtained by resolving the currents into two perpendicular directions, where the vertical component IV is equal to I0 cos phi 0 plus I2 prime cos phi 2, and horizontal component IH is equal to I0 sin phi 0 I2 prime sin phi 2. Where sin phi 0 is equal to sin inverse of cos phi 0 and sin phi 2 is equal to sin inverse of cos phi, and I1 is equal to root over IV square plus IH square. This concludes our discussion for this lecture. In the event that you have any question regarding this presentation, feel free to post them in the comment section and don't forget to hit the subscribe button. See you in the next one.